In this video, we're going to wrap up our discussion of regular ethers by talking about reactions of ethers as well as miscellaneous topics. So in terms of reactions of ethers, there's really not a lot to consider. Many ethers, especially small ethers like diethyl ether, are highly flammable, and they will also form peroxides, which can be explosive. So if you come across a really old bottle of diethyl ether, especially if you see some crystals around it, do not touch it, stay away from it, and call the bomb squad. The relatively low reactivity of ethers makes them pretty good solvents. We've talked about a number of reactions where diethyl ether or tetrahydrofuran are commonly used as solvents because they don't undergo a lot of reactions. One general reaction of ethers is acid-catalyzed cleavage. Now, this typically only happens with really strong, really concentrated acids. So mild acid ethers would be stable. It's only with really, really strong acid that a reaction will occur. So an ether can be converted to an alcohol and an alkyl halide. So how this works depends on the compound itself. If we were to think about this as an alcohol, we would call this a secondary alcohol, and this one would be a primary alcohol. So in the presence of strong acid, the oxygen is going to grab a proton, and we will get
the protonated ether plus bromide. And then the bromide can add here, kicking out the alcohol as the leaving group, giving us this plus this.
If we had a secondary and a tertiary, then we would get our protonated alcohol.
Sorry, I mean ether.
And this one could act more like an SN1 reaction, so that we get this alcohol and this carbocation, and then that could be converted to the bromide, for example.
So typically, though, this reaction isn't very clean because although I've drawn it as giving us this alcohol and this alkyl halide, it's also likely that you will get this as the alkyl halide and this as the alcohol. So you're going to end up with two different alcohols and two different alkyl halides. In some cases, the reaction can be carried out with a large excess of HBr, so that whichever alcohol is formed is then going to be converted to the alkyl halide. So you still have a problem of two alcohols, two alkyl halides as intermediates, and then they would all be converted to alkyl halides. So then you just get two alkyl halides, one from each side of the ether.
But still, this is not a very useful reaction because it requires such harsh conditions. So we're gonna pretty much ignore it. There is another reaction that I wanted to mention, and this is specific to aryl allyl ethers. So our ether, we have an aryl group and we have an allyl group. Now, when this is heated up, this can undergo a pericyclic reaction where we imagine these electrons move here, these electrons move here, and these electrons move here. This is related to the Diels-Alder reaction in that they are both pericyclic reactions, but the Diels-Alder is a cycloaddition, whereas this is called a sigmatropic rearrangement. You're not responsible for this, but I just wanted to mention it. A sigmatropic, this is TRO rearrangement. So following those arrows, what we get looks like this, where we have a double bond O, and now this carbon is connected to this carbon, which is connected to this alkene. So This bond is broken. This single bond is now this double bond. This double bond is now this single bond. And where there was no bond, there is a new bond. Notice what we have is a keto form. So this exists as a ketone. But in this particular case, if it existed as the enol, where here's the double bond and this was an OH, then we would have benzene. So we would actually have a phenol. So this molecule will undergo tautomerization to give this, an allyl phenol. So one reaction that is general but not very useful, one reaction that is quite useful but very limited in scope. So basically, when it comes to reactions of ethers, we are going to use none of them. So there are a few miscellaneous topics that I wanted to mention about ethers because there is some really cool chemistry that happens. So this compound is called 18 crown 6. 18 because there's a total number of 18 atoms, and then 6 because there are 6 oxygens. So this is a systematic way of naming these crown ethers. And these are important because they have a very hydrophobic exterior, but a hydrophilic interior. And depending on the size, they can actually sequester a metal cation on the inside. And the different size crown can hold a different size metal. So for example, 18 crown 6 can hold potassium. 15 crown 5, I believe, is better at holding sodium, for example. So there are some really cool applications of crown ethers. Let's say you are trying to carry out a substitution using potassium fluoride. Well, you get no reaction because typically your F minus is going to be so surrounded by solvent that this cannot act as a nucleophile. If you were to carry out this reaction with KF in a nonpolar solvent such as benzene and in the presence of 18 crown 6, you will convert this to an alkyl fluoride. Because under these conditions, the potassium is going to be sequestered in the pore of the 18 crown 6, and that's going to leave F minus essentially naked because benzene isn't a good solvent, so it won't be effectively solvated, leaving the fluoride very ready to react. Analogous to crown ethers, we have a number of naturally occurring ionophores. This first one is called monensin, and the second is valinomycin. So monensin is a polyether ionophore antibiotic. It has a hydrophobic exterior, and so it can be carried through the cell membrane as a host, but it can carry as a guest a potassium or a sodium ion. By interfering with the normal imbalance of sodium and potassium ions on the interior and exterior of cells, it functions as an antibiotic because it can kill cells. Valinomycin is another ionophore antibiotic. This one is not an ether, though. It is a polyester and a polyamide. But again, we have all of these oxygens that can sequester a metal cation, which can again have an impact in ion transport. Here is an example of a really potent, biologically active polyether natural product. This is called palytoxin, and this was synthesized in the 1990s by Kishi's group at Harvard. Here's the molecular formula, C129H223N3O54, and this is the IUPAC name of this compound. Look at the specification of a number of different chirality centers, and yeah, it's just huge. And so we have a lot of cyclic ethers within here, as well as a ton of other functional groups. It's not that synthetic organic chemists are trying to come up with new ways to make incredibly hazardous substances, but often the efforts to synthesize a biologically active natural product leads to the development of different synthetic methods that can be applied to other types of reactions that might lead to a valuable medication, for example. Here are a couple other really cool polyether natural products. This one is brevetoxin. There are actually biblical references to brevetoxin, which is responsible for red tides. And this is all cyclic ethers throughout this molecule. And then there's a cousin, a much older cousin apparently, of brevetoxin called madotoxin. And so just check this thing out. It is huge. And both of these were synthesized by Casey Nicolau's group. And actually, one other thing I wanted to mention, notice here this RCM. So they're showing the synthetic approach that was used. And so this ring, as well as this ring, were made by ring closing metathesis, something we mentioned a couple of chapters ago.